All right, well, yesterday when I was recording this, my phone got a call and I didn't notice, so the last 10 minutes of this thing didn't record. I only noticed after I uploaded the video because it seemed a little short at 13 minutes. So I'm going to pick it up from here. Two topics left, so solving these exponential equations with radicals in them, and then also we're going to be looking at a compounding growth formula that comes up usually in the calculator part of the exam. So for solving equations that have radicals in them, you're going to need to be able to write these in exponential form. Okay, so back in the day when you learned these, you learned that these are actually fractional exponents, so exponents that have a fraction, and there's a way to convert, say, the square root of 3 into what we call exponential form. So first of all, just a couple things to remember for the square root of 3. The 3, that's called the radicand. That's what I'm going to be calling it. And then we have sometimes an exponent here. So in this case, it's a 1. And then over here, if there's nothing written, it's a 2, and that's called the index. Okay? So if I'm going to write the square root of 3 in exponential form, first I take the radicand, and that becomes my base. Okay? And then I take the exponent, so if there's nothing there, I'm going to write a 1. That goes in the numerator of the fraction, and the index goes in the denominator. So square root of 3 is the same thing as 3 to the power of a half. Now here we got the cubic root, so the index is 3, cubic root of 7. So for this one, I'm going to write the base, which is 7. That's the radicand. There's nothing here, so it's a 1. So I put a 1 in the numerator, and then the index is 3, so that's the denominator, and you have 7 to the power of 1/3. So now we can solve questions that look like this. Now I thought I had cleared the screen before, but I didn't. Give me a moment. Let's try again. Is it all gone? Okay. There. I'm laughing because nothing can ever go quite right today. This is the second time I'm recording this because the first time I forgot to hit record. And then yesterday I got the phone call. So third time's the charm, Here we go. So we got equations like this with the radicals. So now not only do we need to write everything with the same base, but if you see a radical, you need to write it in exponential form if you're going to have a hope of solving it. So on the left-hand side, I can rewrite 2 to the x because that's as simple as it's going to get. Now the 4 I can write as 2 squared. The radical has a base of 2, so I'm going to write that. The power is 1, so that's the numerator, and the index is nothing there, so it's 2. So that's 2 to the 1/2. Now we got to go back to grade 9. Look, you got the same base being multiplied. So in grade 9, you learned you add the exponents. So I'm going to write 2 to the power of 2.5 or 2.5, however you like to write it. Now I got the same base, I can equate the exponents, and I figure out that x must equal 2.5 for that equation to work. Perfect. Look at B. Lots of stuff going on. So a couple of things. When you have an exponent that's more than just a monomial, maybe write brackets around it so you don't forget to distribute things into the brackets. And then we got 2 radicals to clean up. So the first one has a base of 3, the radicand is 3, so I'm going to write 3. And the power in here is 1, so that's the numerator, there's no index, so it's a 2, so it's 3 to the 1/2. Now I wrote the brackets around the x minus 1 because it'll be multiplying whatever exponent is already there. So that one's cleaned up. Over here I got 9 as my radicand, so that's my base is 9. There's no power here, so it's a 1, and the index is 3, so it's 9 to the 1/3. And now I'm looking at the question and I'm like, aha, I need to get the same base before I can equate the exponents. So on this side, we don't need to change anything, but over here, I need to think about how do I write 9 as a power of 3. So that is 3 squared, and it was raised to the power of a 1/3. Now we're back in grade 9, and you have a power to a power, you have to multiply the exponents together. So this is 3 to the power of 2/3. Over here, I'm just going to be lazy and just do that. So just pretend I was writing it. Don't do that on the exam, but in your notes you could. So now I got the same base, so I'm going to equate the exponents. So I'm going to write 1/2 times x minus 1 equals 2/3. Okay, and then happy solving. At this point, we should be rocking and rolling. So here we go. Lots of things that I could do here. I could distribute the 1/2 into the brackets and clean things up. I don't generally like that. That's a lot of work. I can simply multiply the 1/2 away. So if you multiply by the reciprocal of 2/1, then here you'll get 1. Don't forget to do it on that side too. So that cancels out to 1, and I'm just left with x minus 1. Over here, 2 times 2 is 4, 3 times 1 is 3, and you get 4/3. Then I just add 1 to both sides to get x. So add 1, so that's gone. Now when I convert this to a fraction, I get 3/3. So overall, I get 7/3. 4 plus 3, 7. Done. That was easy. Boom. Here's another one. Super tricky, lots of stuff going on. So let's clean up all the bases. Nothing we can do on the left-hand side. Okay, but over here, 8, I can write as 2 to the power of 3. Now I have another radical, so radicand is 2. Power is 1, so numerator is 1. Index is 3, so that's the denominator. I got the same base being multiplied, so I add the exponents. Now you can write it as 2 to the 3 1/3, and you have the same base, and you can leave your answer as 3 1/3, so as a mixed fraction, or if you're like me, you like the improper fractions, so improper, so you go 3 times 3 is 9 plus 1 is 10, so that's 10/3. Either answer is fine on the exam, as long as you got your work, it's all good. Cool, so I think we're moving on now to our last topic, which is basically looking at how all these exponential things get used in real life, very briefly. So you'll see it usually with growth or decay kind of questions. So believe it or not, you see lots of exponential growth things in chemistry, in physics, in biology, with populations and things, and then in financial math. So logs actually, if you look at the history of logs, it's super fascinating. The concept was dreamt up like in the 1600s or something. Didn't become useful until like the 1800s or 1900s. Anyways, I'm not here to give you a history lesson, but I am here to show you this formula, okay, which is on the formula sheet for the grade 12 pre-calc exam. And we're going to be looking at all this growth and decay stuff just in the context of some financial math stuff. Now, we're not 100% ready for the kind of question that usually shows up on the exam. Those ones are algebraic questions, like we need to learn logs first, but I want to introduce you to this formula first, and then as we teach more lessons, you're going to see this coming back, and eventually I'll show you the actual exam questions that you get. Yeah, so here we go. Let's see, compound interest. So a principal of AO dollars is invested at an annual interest rate of I. So AO dollars, that's right here, AO, and that's the initial investment or whatever you have. So initial investment. And it says I is the annual interest rate. So there's I know it's hard to see. Let me clean this all up. There. That's better. Okay, so I is right here, and it's the interest rate. And it does need to be written as a decimal, so I'm going to say as decimal. So if you want to write divide by 100, that would be good. So if they say the interest rate is 4%, you're going to divide by 100 and you're going to write 0.04 as the number you'd use in the formula. So interest rate I with n compounding periods per year. So n is right here. It's in 2 spots in the formula. And I'm just going to say compounding periods. We'll talk about what that means in a moment. So for now, you just know it's this thing called compounding periods. The amount $8, so that's the final amount, after t years is given by this formula. So there's t, and that's time. You just need to watch the units in the question, make sure that all your units are matching. So we'll see that probably in the future. So there's the formula. Oh, and I forgot this one neat little piece. It's like, what the heck is that? This is the number 1. Okay, so it's 1 plus this fraction. So it's the actual number 1. It's not an L or anything. It's the actual number 1. All right. Yeah, AO represents the initial investment. There's lots of different ways. Sometimes, like, they call this the initial investment. Sometimes, I think they call it the principal, I think. And then same thing with A, the final amount. Sometimes they call it the future value. So there's a couple different words they use for A. So if we look at this question here, Not exactly the kind of question you get on the exam, but very, very close. It's all we can do for now, so let's take a look. So it says the future value of $5,000 is invested for 10 years at 5.5% compounding, semi-annually, monthly, daily. So maybe we'll do one of these just to demonstrate, and I'll talk about what compounding is. Let's do B. We'll do B, where it's compounding monthly. So, couple things. This is AO, this is T, and then I is 5.5%, which you need to write as a decimal, so divide by 100, you get 0.055. Now, this N thing, let me just tell you all the different ways that you can that you usually see N. So semi-annually means N is 2, monthly means N is 12, daily means N is 365. Yeah, and that's usually all you really see on the exam is those three. So what the heck is N? It has to do with how they calculate your interest. So let's just say you borrow $10,000 from the bank at 10%, per year, and it's compounded daily. Okay, so what the bank does is they say, okay, well, 10% per year, you're going to give us $1,000 of interest for the year. This compounded daily thing, so what's that? It means that every single day, they're going to split up this $1,000 interest, and they're going to add it back to the amount that you owe. So every day, so the first day you owe $10,000, okay? Then they take this number, we can do it, we can divide by 365, so the 1,000 divided by 365. Okay, so that is $2.73. So day one, you owe $10,000. Day two, they say, at 10% interest, you now owe us $10,000 and plus $2.74. So now you owe us this. And oh, by the way, now we're going to calculate the compounding interest on this. So what they do is they say, okay, you owe us this much money now, and they recalculate everything, and then they tack that amount back on. So this compounding daily idea is that every day we add on the interest that accrued in that one day, and we put it back on the original amount. Okay, so if you're investing money, that's great. It means every day you're getting more and more money. If you owe money, that's bad because your debts can grow quite quickly. And that's what compounding is. If you didn't quite get it, that's okay. At the end of the day, I guess you need to just know how to plug that number into your formula, but that is the concept of what it means. So semi-annually means twice per year we're going to add the interest back onto the amount that you owe us. Monthly means the same thing, that every month they're going to calculate the interest and add it back to the original amount that you owe. So let's do B, see what it looks like in a question, and then we'll go on our happy way, our merry way. So here's the formula. Boom. And we'll type in all the numbers. Now, see if I can remember. So I believe it was $5,000, 1 plus 0.055 over, now the n was 12, so we put a 12 there, and it's raised to the power of n times t, so 12 times 10. I do believe it was 10 years, yep. So all that information is from the question. How I recommend you type it in on your calculator is do the bracket first, just follow order of operations sort of. So bracket first, let's see what we get, 0.055 divided by 12 plus 1. Now, it's going to seem silly, but you're going to want to keep every single decimal point that you get. Every single one. And just trust me on that. Keep every single decimal point you get on your calculator, and 12 times 10 is 120. Now, last thing, so if we're just solving this kind of question, take this, raise it to the power of 120, and I wouldn't write that number, I get 1.731076, keep that on your calculator, and then just multiply it by 5,000, and then write that answer down. So it's 8,655.38. There. All right. So now you have sort of an idea of how the formula works, what all the pieces mean. as the unit goes on, I will show you the question that you'll get on the exam. You're not going to get one of these where you just plug everything in and, that's like a grade 6 question, right? What is going to happen is you're going to be solving for one of the exponents algebraically, okay? So what I'll do today is I'll show you how to do that graphically, which is not something that we do on the exam, but it will give you sort of an idea of what you're actually doing when you're doing it algebraically. So, in this particular example, we're going to solve for time. Okay, so basically we're going to be looking where the compound interest equation intersects the future value that they give us. So let's see what we got. A principal of $1,000, so that's AO, is invested at 6%. So divide that by 100, you get 0.06 for I. It's compounded monthly, so N is 12. To the nearest tenth of a year. Aha, that's what I don't know. When will the amount be $1,400? So that's the final amount. So here we go. Here's my formula. It's A equals AO 1 plus I divided by N to the N tape. Again, you don't need to memorize it. It's on your formula sheet. And they often give it to you in the exam on the question they use it on. So, type in all your numbers. 1,400 for A, 1,000 for AO. 1 plus 0.06 divided by 12 raised to the nt, so 12t. Aha, there we go. So if we were doing this with logs, which we don't know how to do yet, we would clean this all up and then we would do stuff with logs and we'd be able to solve for t. Now that last step requires a calculator to give you a decimal answer. In this question, we're going to be doing it graphically. So we're just going to clean this up in here and then I'm going to notice something that's going to happen. But what kind of graph this is. So 0.06 divided by 12 plus 1. So here we get 1.005 raised to the 12t, and it's 1,000 over here, 1,400 over here. Now look at this graph. That looks really scary, doesn't it? But if you think about it, it's really just an exponential function, right? It's complicated, the numbers are ugly, but it's really not going to look much different than, say, this graph, 2 to the power of x, right? This number is bigger than 1, so we know that this graph is going to be looking something like an increasing function, right? We got a number out here that's multiplying it, so, if I was getting you to graph it with pen and paper, I'd make it a smaller number like 3, and yeah, I could put like a 2 in front of the x. At the end of the day, it's still this increasing function that's going to look like that. What about this side of the equation? Well, if you look at this is your y value. So this is y equal $1,400. So that's a horizontal line. So when I graph this, I'm going to have time on the x-axis, I'm going to have money on the y-axis, and the answer is, where does the line $1,400 intersect my exponential function? That will be the answer for time. So that's what we're going to do graphically. I guarantee you it's going to look something like this. This is going to be really steep because of the 1,000. Like it's probably going to be like something crazy like that, okay? But it's still going to be an increasing exponential function. Let us switch to Desmos and see. Now I've been clever because I've done this 3 times now, and I already input all the equations. So here's our exponential function, the red line. You can see it's super steep, and we got it here on the negative x values, and if we scroll up, eventually we cross over into the positive t's. Okay, and then I typed in the equation for the line y equal 1,400. I'm just going to zoom in here. So there's $1,400. The red line is my exponential function, and boom! It'll take. Is that a 5? It's 3.622 years. So that's the time. I'm going to check out my computer. No, it's 5. It's 5. It's hard to see on the projector, but yeah, 5.622 years. So that's when we'll reach $1,400. Eventually, we'll do this algebraically. I just wanted to show you today what it looks like graphically. And that's really it. This is a try it yourself, same question, different numbers. Sometimes we do see decay questions, right? Like in our formula when the b value is between 0 and 1. Now for those kinds of questions on the exam, sometimes they just give you a weird equation and it'll be on the calculator part and it'll ask you to do something with it. I'm going to leave that for today. I'm not going to do this question. We're not going to be doing it graphically, so I just did one just to show you. And you guys can now finally do exercise 5.3. Okay, For the third time I'm recording this. Bye-bye.